I don't wanna grow up, I'm a curious kid. The world has 100 questions I can play with. So I'll open my arms and eyes and wonder every day till the day I die. No one really knows why gravity exists.
Good evening, everybody. Welcome to Wonderfest. My name is Tucker Hyatt. I'm the founding director of this Bay Area beacon of science. And I am grateful. I'm grateful that you are here. I'm grateful to HopMonk for hosting us. Stephanie Reeves is a researcher and PhD candidate in the School of Optometry and Vision Science at UC Berkeley. Go Bears. Stephanie earned her bachelor's degree at Connecticut College, where she was a triple major in neuroscience, Slavic studies, and dance. Maybe we'll get to see all three of those tonight. She then went on to study vision in patients at the Massachusetts Eye and Ear Hospital. Now at Cal, she uses head-mounted high-tech gadgetry, that's not its official name, to help understand eye movements and vision. Please welcome neuroscientist and Wonderfest Science Envoy, Stephanie Reeves.
Hi everyone. Thank you, Tucker, so much for the lovely introduction. It's really great to be here with all of you tonight. Can you hear me all right? Yes. Excellent. Okay, without further ado, let's hop into the science. In our everyday lives, we experience and capture scenes like this every day. You're going on a hike with your puppy, it's a beautiful day, you're sitting at your desk doing your PhD. You're going to a baseball game and it's your first time there as a 30-year-old. You bring home an egg from ramen. You're with your husband at a park, or you're visiting with friends. I wanted to start with these pictures not only because they're cute and they're from my daily life, but to make the point that humans are visual creatures. A major way that we experience the world is by using our eyes. And while you might look at these images and immediately understand them, one huge reason you're able to do that is because you're moving your eyes. So picture this. You're visiting New York City and it's your first time there. You're driving down the road trying to figure out where to go next. In order to navigate safely, you need to look at potential moving cars, road signs, and pedestrians. And so this video mimics someone doing exactly that. One big reason we need to move our eyes is because the resolution of our vision is not uniform. So the back of your eyeball contains your retina, which has these photosensing cells that enable you to see. And an image of some of those cells are shown here on the left. Interestingly, because these cells are denser in some places than others, what that results in is better vision where you're looking and worse vision where you're not looking. So where you're looking at 0 degrees of retinal eccentricity, you have high vision, high resolution vision. But even just a little bit off center in your periphery, your visual acuity drastically drops. To put that into perspective, 10 degrees here is about a fist width at arm's length. Okay, so I've been talking about the importance of moving your eyes, but what do I actually mean when I say that? So there's a lot of different types of eye movements that we make, but the main eye movement that I've been talking about so far is called a saccade. A saccade is a fast eye movement that helps to redirect gaze. Okay, so I'm gonna do a little demo and have everyone take out their cellular devices. and flip it onto the camera portion. And then imagine you're like taking a selfie. Look at yourself in your phone, and you have to hold it up pretty close, 6 inches maybe. And then look at your left eye and then your right eye. And you should be able to see that fast movement. Can people see that? Yeah, try to hold it close. If, yeah. Is that working for people? Okay, I'm seeing some nods, some murmurs. Excellent. Did you get it? Yeah, okay.
I don't get it, sorry.
Okay, yeah, your phone's a little far. Try to put it really close, like 6 inches or so. Even closer than that. Yeah, and then just look at the left eye, then the right eye. Left eye, right eye. And you should see, as you repeat that, your eye make a fast movement. Did you catch it? Awesome. Yay. So those are your saccades. Now I'm going to give you some homework. Tonight, do that same task in the mirror, and you won't be able to see your saccades. So the only reason why we're able to actually see our saccades is due to the latency of your camera on your phone. So, homework for y'all. Okay, so saccades are very fast. They're maximum 800 degrees per second. We make them 2 to 3 times every second that we're awake. Importantly, they're crucial for quickly looking at something with that really good high-resolution vision that I was talking about earlier. Saccades are generated by the brain. They tend to be smaller than they are bigger, and they also tend to be horizontal than in other directions. Saccades are also really important for preventing visual fading. And I'm gonna just do one more demo with you all, bear with me. I'll have you stare at that red dot in the center there. Let your eyes fade, kind of like relax. And what you should notice is that the ring around that red dot fades. I'm seeing some nods in the front row. Does it work in the middle, back? Okay. Yeah. So people have found that this fading that happens is related to a reduction in your saccades. So saccades are really important for preventing visual fading. Okay, so I've been telling you now a couple facts about saccades. How did people come to know this information? So what researchers have done over the years is to measure eye movements using an eye tracker. And what happens is that people will participate in research. They come to UC Berkeley or to Stanford or wherever, and they consent to participate in research and consent to eye tracking. When you're eye tracking a human, you can either have one that's mounted on their face, like glasses, or one that sits on a table. And then while their eyes are being tracked, they're doing some task. Maybe they're looking at an image, staring at a dot, doing something related to what you're interested in. Okay, so we have found that when people look at images, where they look is not random. So on the left here is an image, and the white lines indicate where that person was looking. So you can see that people tend to look at faces, interesting objects, the ground a little bit, right? So not every place in the scene is equally likely to be looked at. And when you measure the direction of each of these saccades, what people have found is that they tend to be more often horizontal than other directions. And that's illustrated by this plot on the right here. So you have the direction of the saccade on the angles, so up, right, left, down. And then the radius represents the saccade frequency, how often they're happening. So this plot means that saccades are happening most often to the right and to the left, and less frequently in the oblique directions and vertical directions. And people have also studied this in patients. So on the left here is a plot, a polar plot that I just showed you, from healthy controls. And they have this nice, what's called the horizontal saccade bias, that predominance of horizontal saccades. And these other diseases evoke different horizontal saccade biases. And so one reason why it's important to understand this horizontal saccade bias in healthy humans is because it might help us to be able to detect and track the progression of certain diseases in patients. Why are saccades horizontal? No one really knows, but it's been a huge part of my dissertation. Saccades could be horizontal for a number of reasons that I'll tell you about now. One possibility is due to our eye muscles. So each of our eyes has 6 eye muscles that control how our eyes move. To make a horizontal saccade, you only need 2 of those muscles. But to make a saccade in any other direction, you need additional muscles. So potentially, it's just more efficient to make horizontal saccades, muscularly. Another possibility is that this horizontal bias in saccade direction is due to language, reading habits, culture, right? I'm speaking to you right now in English, and we read from left to right. So maybe that has some influence. And lastly, we know from decades of research that our world has orientation regularities and has certain patterns in it. And so potentially due to the statistics of the natural environment, our eye movements have evolved in the way that they have. Important to note, these possibilities are not mutually exclusive. Okay, so it's 2021. I'm learning about saccades. I've just started out in a new lab with my PI, Jorge. We go on hikes like this, and I'm learning a ton. He's teaching me all about vision science, but also this thing called the vestibular system. So the vestibular system is in your ear, and it's responsible for helping you maintain balance and spatial orientation. The vestibular system is also important for certain types of eye movements, especially when you tilt your head. And so I'm here learning about the vestibular system and saccades, and I start to wonder if maybe there's some relationship here. And I start to wonder, why are saccades horizontal? Could it have to do with our head orientation? And so what we hypothesize is that maybe these horizontal saccades are related to head orientation. We're upright beings, right? We're all looking at me with our heads upright, not like laying down. When we're driving, for example, and looking at the car in front of us, we know based on experiments that there are certain places where we're likely to look next, but we only know that from experiments when the head is upright. But what happens when the head is tilted? Maybe in those times when you're chatting with a friend and you're cocking your head, or when you're going around a turn and following the turn with your head. Would the likelihood of a place that you look next be the same or different in this head position? No one has really studied this. But understanding how head orientation influences how and where you look could be important for mitigating accidents and informing better design choices in our roads and highways. So let's conduct a human subjects experiment to test whether head orientation influences the horizontal saccade bias. To study this, we recorded eye movements during a free viewing task. That just means that we have people come in and they look at a picture. And they look at a picture while their heads are upright and while their heads are tilted. To do this, we used virtual reality. The pictures that people looked at were pictures of normal scenes that we would see in our everyday life. And like I mentioned, we used virtual reality to do this. And that was really cool because the scene took up the entire field of view. So it felt almost as if you were really immersed in the scene. Importantly, this virtual reality headset was also equipped with eye tracking. So it's really easy to just export the data. Okay, so we know that when the head is upright, saccade directions are horizontally biased. That's what we know. But what about when the head is tilted? One possibility is that there is no influence of head orientation. The other possibility is that there is an effect of head tilt and that the saccade horizontal bias rotates to either fully or partially align with the head. Raise of hands, who thinks option 1 is likely to happen? Okay, got a couple. All right, raise your hand if option 2 is likely to happen. Okay, slightly more, maybe 60%. Okay, let's see. So when the head is upright, we get this nice horizontal saccade bias, as we would expect. But what happens when the head is tilted, let's say, to the right? This is the distribution. Some similarity, but some differences too, right? The distribution looks a little more tilted in alignment with the head, offset just a little bit, right? Not like a perfect match. And in the direction of the head, importantly. And so we found the same thing with the head tilt in the other direction. And then, since we're scientists, we wanted to measure the offset in these distributions and find out like a number. So when we did that and we measured the offset, the difference in these distributions, and when we plotted that on an index from 0, meaning no head tilt influence, to 1, meaning complete full head tilt influence, what we find is that the saccades are somewhere in between, but importantly are, different from no head tilt influence. So there is some head tilt influence, but not 100%, let's say. Yes?
What if you take a picture that's not a left-right picture? A picture that's more a vertical picture or a spherical picture?
I love that question, yes. So,
is there some interaction between the type of picture and what you would target with the saccades?
Absolutely.
Stephanie, you mind repeating the question?
Yes, repeating the question. Is there an influence of the type of scene that you're looking at? For example, what if you look at a scene with more vertical contours, or sort of a different type of scene without so much horizontal information? We ran that experiment using these fractal images, which are radially symmetric. So they're just kind of symmetric, they have no strong orientation cues, and you find that this metric is a bit higher. So what you're looking at absolutely does also play a role in how saccades are generated, both the head and what you're looking at. Yes?
So, using the VR headset, were the images that people were seeing tilting when they tilted their head?
No.
Okay, good, because that would seem to me to confound.
Yeah. Sorry, to repeat the question. The question was, when the head was tilted, was the image presented Earth upright or also tilted aligned with the head? And the answer is, the image was presented Earth upright. Yeah. Okay, so yeah, in conclusion, we use saccadic eye movements to see the world around us. Saccades tend to be horizontal, and saccades are horizontal because of the eye muscles, reading, language, the statistics of the world, but also, importantly, because of our head orientation. Understanding saccadic eye movements in healthy populations may help diagnose or track disease progression in patients such as Parkinson's or PSP, as I mentioned a bit earlier. And understanding how humans prefer to look at the world in natural settings may help inform the design of display technologies. Thus, additionally, studying eye movements when the head is not upright also improves our understanding of how the brain combines information from multiple reference frames. Okay, I'd like to thank my lab, first and foremost, pictured here on the left, for helping me along my PhD journey and supporting me along the way, and integral as well to Wonderfest and Tucker for the introduction and invitation, to the HopMonk folks who made all this possible, and to all of you for being here and listening. Yeah, I appreciate it so much. Lots of questions. I love it. Yes.
What happens if the image is tilted?
Can you
Yes.
repeat the question?
Or
So this is
if
tough.
the image is vertical, like the Eiffel Tower,
Mm-hmm.
and the head is not tilted?
Good question. So the question was, the first part of the question was, what happens if the image is tilted along with your head? In that case, both the head and the world are aligned, and we did actually run this experiment. And so what happens is the saccades are just directed in sort of that same orientation with respect to both the head and the image.
What I was referring to is that the image is tilted and the head is upright.
Ah, yes. And that, okay, so then the second part of the question was, what about if there is image tilt and the head is upright? In that situation, you get a similar result in that the saccades are executed somewhere in between the orientation of both the image and the head. Does that make sense?
What about if there's just a vertical thing like, say, the Eiffel Tower or the Leaning Tower of Pisa, and I don't care which way your head's tilted?
The question was about what if you're looking at the Eiffel Tower or the Giza, the Italy one, what happens then? I'm honestly not sure about that one, but good future experiment. There was a couple other questions, yes.
I am really excited about you and your saccades and a practical use of them. I am a former television producer. I look at things with that wide screen and horizontal, and our vision is really more horizontal. I'm looking forward to you and your work changing Instagram to be horizontal instead of vertical.
You don't need to repeat that. That was well said.
Yeah, I look forward to that too. That would be nice. Thanks for the comment. Yes, question in the back.
So I went to Johns Hopkins for graduate school. There's a lab there called the Robinson Lab that's worked on this for 40 years or something. And they would put a coil on a rhesus monkey's eye and then record the brain as they did saccades. Does a monkey that not used to our reading have the same orientation of the saccades, or are they different?
Great question. So the question was, this gentleman studied at Johns Hopkins, knows David Robinson, and is aware of studying monkeys and their saccades. And the question was, do monkeys have these same saccadic biases, directional biases? Yeah. And the answer to my knowledge is that not enough research has been done on that. People have asked monkeys to fixate and then looked at their saccade directions, and they're predominantly vertical. Monkeys live in trees, they have a different, seen diet than humans do, so that could play a role. But to my knowledge, no one has asked monkeys to look at pictures, for example, and then measured saccade directions. So that would be a good project. Yes, a couple more.
I was guessing that our horizontal bias may have come from evolution, because if we evolved in an open savanna, that's a horizontal world. If you evolve in a forest or a jungle, that's a vertical world. Predators can be above or below, prey can be above or below, food can be above or below. But in the savanna, things are just in a two-dimensional distance. As the monkey would have a vertical orientation because they need to. And we have a horizontal orientation because that's where we became what we are. It's just a theory.
Totally. I think, yeah, the point was about just, again, the sort of visual diet differences between humans and other animals. And I think you're hitting the nail on the head that those differences can play a role in how our behavior has evolved. Yeah.
Is there any difference between people who learn to read in Asian languages, where the language is arranged vertically instead of horizontally? Is there a difference in the saccade behavior of these people?
Yes, the question was about if saccade directions change in Asian languages, for example, if they're more vertical instead of horizontal. I believe there was one experiment in the 90s that looked at that, and I think they found some differences. Not sure if people have replicated that effect, but that group did find it. Yes.
Thank you. Is anything being done with the saccade research on how to help people who have vision impairment to be able to see better and learn to, adjust their saccades?
Great question. The question was about if any research on saccades is being used to help people with vision impairments that lose their vision, and you can't correct it just with glasses, right?
Right, yeah.
So yes, there are definitely researchers working on this. There's one project that I know of that actually was working to train folks with a type of vision impairment that's almost a brain deficit too, from stroke. And it's like an inattention to one side of space. And what they did was they had people watch movies with a region of the movie highlighted on where to look, and they instructed people to follow that area with the hope that it might, encourage those people to look more onto that neglected side.
Did it?
I don't remember.
You don't remember.
Yes.
Has any work been done with saccades and the changes in the bias with dementia?
Yeah, so the question was about changes in the saccade bias with dementia. I don't remember off the top of my head, but certainly, other neurodegenerative disorders, like I mentioned, Parkinson's and PSP is also a neurodegenerative disorder. I believe they might have looked at it in Alzheimer's too, some groups. So, but I think that could be like an interesting new avenue of research, right? To study that more explicitly, and then maybe, if people are just doing natural looking around in their daily life, and then you find out your eye movement patterns have changed, that you could get some message and say, go to the doctor or something like that. So, a couple more questions. Yes.
So I have the answer to this, but I want to hear your take on it.
Good luck.
Most windows in a house are tall and skinny, but we view things horizontally. Do you know why that is?
The question was, windows are vertical, but we look horizontally. Why is that? I don't know why.
I was told at a seminar years ago, somebody traced it back to castles when they were defending the castles with bow and arrow. And they had tall, skinny windows to shoot at people.
Oh.
So that's how slow things evolved in the building business.
That's amazing. Yeah. I'm just picturing now everyone shooting bows and arrows outside of windows. That's fun. Yes.
So it sounds like your test condition was, what's being looked at is always at a constant distance in a stereo fusion sense. Do you have any ideas that would be different in the real world where things are at distances? So two eyes now have to do something slightly different to maintain that stereo fusion.
Great question. The question was about that this experiment is at a fixed distance, but in the natural world, we see in depth, and so our eye movements do make different patterns to control for that, to help with that. Yes, so people have looked at the saccade horizontal bias in more natural tasks, such as grocery shopping, navigating on the road, browsing on a desktop computer, and they all sort of find this similar trend that saccades are predominantly horizontal, though the task does seem to matter a little bit. Sometimes there's more vertical ones, for example, when you're obviously browsing your phone or something, right? Yeah. Last question? Mm-hmm.
Back, I guess, more than 20 years ago, I participated in a study at Google where they watched my eye movement, matched them while they had me look at screens. And I think that they used that information to make sure that what people predominantly look at is what they want to sell or I just tell you that this information has been out there for a while, they just haven't codified it yet.
Yeah, okay, so the question is about, I guess, is it about using eye movements and where people look related to advertising and making that link? I know I think people do think about this, but I'm not sure, I guess, the current state of those research projects, but certainly, you know, it makes sense for those big companies to want to sell all their stuff and make you look in certain places and whatnot, so I'd imagine there's some connections there, yeah. Does that answer your question? Kind of, yeah, okay.
All right, thank you. We'll take a quick break here.
Thank you.
Viraj Manwadkar is a researcher and PhD student at Stanford University, where he studies the very smallest galaxies, and among including their connection to the mystery of dark matter. Viraj earned his undergrad degree in astrophysics at the University of Chicago. At and around Stanford, he organizes stargazing events and is passionate about making science research more accessible and equitable. Please welcome astrophysicist and Wonderfest Science Envoy, Viraj Manwadkar.
Thank you, Tucker, for the wonderful introduction. Is this okay volume? Yeah. Okay, cool. So I'm going to be talking about tiny galaxies and big cosmic mysteries. Since the very beginning of humanity, we've always wondered, why are we here? What are we made up of? And like from our very early conceptions of, maybe earth, wind, fire, and water, to our more modern picture of like atoms, protons, neutrons. We've come a long way, but we still ask the same question. What is the universe? What are we made up of? And one of the most fascinating points about this current picture is that everything we know about you, me, us, we see, we can touch, we hear, is all only 15% of the entire material budget of the entire universe. So that's only 15%. So this other 85% was what we call dark matter. We have no idea. It's zipping through us at this very second in large amounts, but over the past 50, 60 years, we've come a long way in really trying to understand what it could be, but still the big question of what it is remains. And we've understood some key properties of this. I won't go into much about the evidence, but I'll describe the key properties. And so we know that dark matter only interacts through gravity and nothing else. It does not interact with light at all, hence we also call it dark matter. So it only interacts with other material through gravity. We know that it's not very smooth. It's throughout the entire universe, it likes to clump up, and it's very clumpy. And the center of each of these clumps is a galaxy like our galaxy. And finally, we actually know pretty well how it behaves, how it moves in the universe, and how it evolves. But we really don't know fundamentally what it is. And here's a cool graphic, just like sort of talks about the different models. But anyways, it's a huge range of uncertainty in what it could be. And so that's a big question scientists right now are trying to answer is what is dark matter? And so I'm going to boil down this question of what is the universe made up of to a more specific question of what is dark matter? And my second big cosmic question is, why do we exist? And as you may have guessed, there are many layers to this question. One could ask, why does life exist? One could ask, why does intelligent life exist? One could be, why does the Earth exist, the sun, and so on, so on, so on. But I believe there's some more fundamental question, and there could be more, but this is one of them, is why do structures in the first place at all exist in the universe? Structures like our galaxy and all the way down. And the idea is that without galaxies, there would be no stars, there would be no sun, no Earth, and no us. And so the question that I'm going to boil this down to is, why do structures like galaxies exist in our universe? How did the very first galaxies form? And the solution, or not the solution, one way to answer these questions is to study these tiny galaxies. We also call them dwarf galaxies, and they can help us answer this. And when I did a quick search on tiny galaxies, I found this. Just want to say, this is not what I'm talking about. Tiny galaxies are these little two smudges like that. So if you've ever had the privilege to go to the southern hemisphere, I have not yet, and if you look up the night sky, you will see these little two faint smudges. These are called the Large Magellanic Cloud and the Small Magellanic Cloud. These are the two most prominent tiny dwarf galaxies in our galactic backyard. So they're sort of near the Milky Way, our own galaxy. They're sort of going around it, and they're the two most prominent ones as we see them with the naked eye. And just for context, this sort of vertical, dusty line you're seeing is the Milky Way. I'm sure many of you might have seen this. California has some very beautiful dark skies, but if you haven't, I would highly recommend it. It's a spectacular sight. And this photo was taken in Australia, by the way, because you can only see this too from the southern hemisphere. So if you also haven't gone, I would recommend that trip for me as well. So in addition to these two, there are actually many other dwarf galaxies we know. The LMC is the one I just talked about there. It's the largest one, but they come in all shapes and sizes. They're all not the same. So here's just sort of a panel showcasing their beautiful diversity. And one thing I would point out is that they're vast spread in how big they are. So the one at the bottom left, that's if you take that circle and you put it up in the biggest one, it's going to be that small. So even when I'm talking about tiny galaxies, they're not the same at all. It's a huge spectrum. And so to really understand, I feel like whenever I give a talk, people ask, okay, you talked about a light year, but how really big is a light year? Like, it's hard for human beings to comprehend such scales. And so I'm going to use a fun analogy, hopefully, to better convey that. So I'm going to try to convey the sense of scale between Earth and the Milky Way. And so yeah, so that sort of horizontal dusty line again is the Milky Way. And those pointer, ooh, yes. Those two little smudges are those LMC and SMC we talked about. So imagine a grain of rice is 10,000 miles. So our entire life is confined to, you could say, a mere 2.5 rice grains. That's the circumference of the Earth. Now let's take it a step further. Let's say the distance to the sun. How far is that? So using the same scale of one rice grain being 10,000 miles, the distance to the sun is around a 16-ounce glass full of rice grains. So you take those and you put them end to end, and that's the distance to the sun. And now, here comes the real shocker, is if you now, I'm sure you might have gone to Costco, you have to take a Costco, fill it up from floor to ceiling, every little nook and corner of Costco, you take that many rice grains and you put them end to end, that's how much you'll need to traverse, that's the distance you'll have to traverse to get across the Milky Way. So coming back, our little mere 2.5 Earth rice grains and the entire Costco full of rice grains. That's the scale difference between Earth and the Milky Way. And these tiny galaxies, they're not that tiny after all. They're short of, 4 truckloads of rice, but that's still, pretty small than an entire Costco. But these tiny dwarf galaxies are in a full spectrum between 4 truckloads of rice to somewhere like a big shop, but not big as Costco. And so hopefully that conveys, a sense of how, even though they're tiny dwarf galaxies, they're still quite big and they're come in a full range of sizes and shapes. And I'm going to try to now tell you a story about how these exist in our paradigm of what the universe is and how it evolves. And so this is a beautiful simulation run by members of my lab at Stanford. This is a dark matter simulation of the Milky Way and its environment. So this little bright thing in here is sort of supposed to be the Milky Way. And it's a little counterintuitive because when we think of dark matter, we think of it being dark and sort of, black. But here it's sort of inverted. When it's light, that means it's more dense. There's a lot of dark matter there. And the darker patches are where there's less dark matter. So it's a little inverted. So just, yeah, so the Milky Way is sitting in the center, and you have these, and you have this local environment. And you might notice it's not quite smooth, it's clumpy, as I sort of alluded to before. And in each of these little clumps resides a galaxy, like these dwarf galaxies. And the bigger the dark matter clump, the bigger the galaxy inside of it. And so these tiny galaxies, the tiniest of them all, they reside in the tiniest dark matter halos. And another interesting fact about these dwarf galaxies is that they're some of the oldest known galaxies. We also call them as fossil galaxies. And that is interesting because you can then, it's sort of like, how we excavate bones from the Earth, and that tells us the story of how Earth was in the past. Similarly, astronomers go out there, find these fossil galaxies, and that gives them a direct insight into what the universe was like in its early heydays. And so, just to make the picture a little more dynamic, here's a similar simulation, not the same one. I'm going to play it. And this is sped up over the course of a few billion years. We did not wait the full end to let it run. And you can see each of these tiny clumps, they sort of are gravitationally tugging on each other. They come close to each other, and they sort of merge to form a bigger clump over here eventually. And so the idea is that the biggest clumps we see, like the clumps in which our Milky Way galaxies sit in, are formed from these tiny clumps coming together and forming a bigger clump. And hence, coming back to the story of these tiny galaxies, why they're so important, is because the Milky Way is formed by these many tiny galaxies coming together, forming a big galaxy. And so, to sort of make this more explicit, why they are so useful for answering these two big cosmic questions I mentioned before is first, the tiny galaxies, they occupy the smallest dark matter clumps. And this is specifically interesting is because we have a bunch of different models out there for what dark matter could be, and they all give very similar predictions on the largest scales, but they diverge on the smallest scales. And if we have observations to pin down what dark matter is doing on the small scales, we can hopefully figure out what dark matter really is. And so that's why people are really excited about these tiny galaxies. And second, as I mentioned before, is they're the oldest structures. We also have fossil galaxies. And so that gives us a direct insight into how the very first galaxies formed, because these were the first galaxies formed, and they stuck around till now for us to observe them. Thank you to these dwarf galaxies. Yes?
Raj, do you mind questions during your presentation?
Absolutely. If you have any questions, yes. I might have missed a few hands. Yes?
Where is the gravity portion? What makes this thing all kind of fit together?
Can you repeat it?
Yes. So the question, if I understood correctly, is how does dark matter have gravity, and how does it fits into our understanding of other matter? Is that an accurate question? So that's a good question. Our current understanding of gravity, we know, comes about from mass, and our current understanding is that mass comes about from this interaction with this particle called the Higgs boson. And so any particle that interacts with the Higgs boson gets this mass to it, and it can, with this mass, influence what is called space-time, and that's gravity. Dark matter probably does a very similar thing. It interacts with the Higgs boson and gets mass, and hence makes gravity. But beyond that, any sort of detail would really depend on what is the fundamental particle nature of dark matter, which we really don't know. There's a huge uncertainty in it. And so, yeah, hope that sort of gave some insight. Yes?
Do small galaxies shrink, or are they inherently small?
That's a great question. So the question was, do small galaxies shrink, or are they inherently small? Sort of both happens. So when they first start off, they are inherently small, and they can eventually grow with other things merge into them. But also what happens is, let's say your galaxy just entered in the environment of a bigger galaxy. The bigger galaxy has more matter, more gravity, so it can grab stuff from you, and it can sort of make the smaller galaxy shrink. So it's a competing force of, whether you're gaining more matter or you're losing more matter. But the idea is that they all start off small, and they can either grow or just stay the same or shrink more.
And does that mean that dark matter, it grows and shrinks with the galaxy?
Absolutely, that's a great observation as well. Yes. So the observation was, does dark matter also shrink with galaxies? Absolutely, yes. So the galaxy is embedded in the center of this dark matter clump, and the dark matter clump actually extends way beyond the reach of the galaxy. And so whenever a galaxy in its clump is moving towards a bigger galaxy, what is first taken away is actually the dark matter. And once a lot of the dark matter is shredded, then the galaxy inside is sort of exposed, and then that also gets sort of shredded. So yeah. Yes?
This is not a photograph, this is a simulation.
Yes, this is a simulation, yes.
But it's based on information that we've gathered about the location on a cosmic scale of dark matter, which we can't photograph. By what means, can you tell us how we've come to know that there are these fine filaments and huge clumps of dark matter?
It's a great question. So the question was, we really don't know at the very fine scale where dark matter is clustering, so how can we make the simulation? It's a great question. So the simulation is not the exact same as our universe, but it is same as in the sense that it is statistically the same and has the same physics. So if I were to run the same simulation again, I might get slightly different positions, or if I have a different set of initial conditions, I'll get a completely different looking universe. But statistically, as in how many big clumps you have, how many small clumps you have, how far apart are they, all sort of on a population level, they're the same. And that the population level information is influenced by the fundamental physics, which we know pretty well. And so in that sense, they are similar to our real universe, but not at a halo, or not at a clump by clump scale. Hopefully that answered your question.
Let me see if I can refine the question without being annoying.
Yes, please go for it.
Okay. Let's suppose this is what we might call our local group of galaxies here. And so we look with an ordinary camera and telescope, and we can see the local group shining in light. But from that, those pictures with light or other parts of the electromagnetic spectrum, somehow we infer from their behavior where the dark matter is?
Yes. So the question was, how do we infer about where dark matter is from sort of normal light we see, because we don't really see dark matter? That's a great question. So there are many different ways in which we have done that. The most fundamental of them being, that was sort of how we first came about the discovery of this thing out there, is we observed stars moving around very fast, and faster than they should have been moving if the matter was just the matter we see. And so that hinted at some missing component of mass out there that was unaccounted for. And we can use the same principle of how stars, how fast they're moving, to map out this unseen matter, this dark matter. So that's one way we can figure out in our local environment, because we can't really see stars very, very far away, but in our local environment where we can see individual stars and how fast they're moving, that allows us to map out dark matter in our local group. There are also other ways people use this thing called as gravitational lensing, which essentially you see how light is being bent by matter, and some of this matter is this dark matter. So there are many different ways in which you can sort of actually map out the structure in real life.
Thank you.
Yeah. Yes, question?
How do you know that dwarf galaxy is old?
Great question as well. The question was, how do you know a dwarf galaxy is old? So it's sort of like how we do carbon dating on Earth. We sort of look at the abundance of carbon and so on and so on. It's not the same thing, but we can measure the age of a star. A star is sort of like a clock. When it's born, it has a very specific path it takes in its evolution. And if we look at a star, we look at its properties, we can figure out where exactly it is in its history. And that gives us an age since when it was formed. And so a galaxy essentially is formed when stars are formed in it. And so the stars are essentially, you can age these stars and figure out they're very old. Another indicator of them being very old is they're very metal poor. So I'll take this a second to explain this. So all of the metals we see around us, like carbon, oxygen, iron, so on and so on, are all formed inside stars or when stars explode. So if you have lots of stars exploding, you have lots of metals. And so the newer stars will be metal rich because they've had lots of stars in their past explode. But the very first stars, they were the very first stars. There were no stars before them to explode to make the metals. And so metal poor stars, stars that have very little metal in them, are also going to be very old stars. And so if you can't age the stars, you can also look at the metal content of them and use it as an indicator for how old they are. Hopefully that was helpful. Question?
Silly question, but is any of the metal? Can we get any of that metal?
The question was, can we get any of the metal?
Well, wait, remember, to an astrophysicist, a metal evidently is anything heavier than helium.
Yes, so we have a very broad definition of metal. I probably should have clarified that. But to answer your question, seems unlikely. Stars are giant balls of fire and gas. If we try to get close to it, it'll burn us. So yeah, I think that's an unlikely possibility. People have been thinking about doing that for asteroids. They're not giant balls of fire, so that seems nicer. But yeah, stars seems a little harder. But also, a lot of this metal is locked inside, so you have to really go digging in the star, which seems very unpleasant. Yeah. If no more questions, I'll continue on. Oh yeah, question, yes.
So this seems like an aggregation mechanism in the universe, and that we're told the universe is constantly expanding and will only be more isolated far into the future. And at least intuitively, they seem to be opposite forces.
That's a great, so you were hinting at the fact that the universe is expanding, but what all I've been talking about is something contracting, like gravity pulling together. And these are indeed the two competing forces. And eventually, one of them will dominate. Currently, the other one, this expanding force, is more dominant. But in our sort of local neighborhood, this expansion force is not very dominant. So for our galaxy properties and everything, assuming that gravity is the contracting thing is the more dominant one is the correct picture. But maybe towards the end I can talk a bit more about this dark energy, this expanding thing later if you have, yeah. Okay. So to quantify this picture, well, not quantify, to be a little more clear about this picture of how dark matter impacts these tiny galaxies, here are two simulations. The left-hand one is what is called cold dark matter, and the right one is warm dark matter. The cold and warm is essentially a reference to when dark matter was formed, how fast it was. Was it very slow? It's going to be cold. If it was very fast, it's going to be warm. And so you can imagine if the dark matter was very warm, it's going to be zipping around real fast, and it would not want to clump together. But if it was very cold, it doesn't have a lot of energy, so it would want to clump, or it would clump together more. And that's exactly what you're seeing over here, is cold dark matter. You see all this beautiful structure, so many tiny, tiny clumps all the way. But warm dark matter, you only see the biggest clumps. And essentially, so this means that you're seeing more of this small scale structure in the cold dark matter instead of warm dark matter. This means you'll get more tiny galaxies in cold dark matter instead of warm dark matter. And so you can exactly use sort of the senses of these tiny dwarf galaxies and also their internal properties to figure out what dark matter is. And so I'm going to talk about very recent exciting work that I've been doing, like as of a few months old, so it's very much in the works. I've been working on this instrument called the Dark Energy Spectroscopic Instrument. It's in Kitt Peak, Arizona. That's the telescope down there, and it's an amazing instrument. And I'm going to hopefully convey quickly how cool it is. So what is DESI doing? DESI is making the largest ever 3D map of the universe. And so what it does is it's mapping out nearby galaxies, and it's going to observe tens of millions of galaxies. The thing is, that's a lot of galaxies. How do you do that? That would take a long time. People did the math. It would take 20,000 years to do that. We're not going to wait around 20,000 years. The way to do it is with an army of these 5,000 robots. And here's a video that actually shows it. So this is sort of the telescope itself, and each of these things moving is a robotic arm that can point to any direction in the sky and observe a galaxy. And each of these robotic arms moves such that they move in a coordinated fashion so they don't run into each other, because that would be an issue, that would break the instrument. And so then you can move them and you can point each of the little tiny things you see up on the top. That's an optical fiber that points to a galaxy. It observes its light, and you can use that to measure its distance and other properties. And so this is a map we just released a month ago. So this is really new stuff. This is real data. This is not a simulation. This is not an artistic impression. This is real. Each point here is a real galaxy. It has been color-coded for effects, but the color is not important. The position is your real position in the universe. And we're sitting in the center, and each of this is a real galaxy. And some of these are tiny galaxies which I talked about. And specifically, around 200,000 of them are very tiny galaxies, of the 20 million we observed in our first year. And as you can see, the red dots, kind of hard to see, but they tend to be close by, and it's because tiny galaxies are very small, very faint. You can't see them very far, so they tend to be, you tend to only observe them close to you. And so this is a quick picture I made actually today morning of the latest data we have on tiny dwarf galaxies that we have discovered. And it's a little cute. I find this picture very cute. It's like little faint smudges in the sky, all different colors. And we have assembled, and in process of assembling, the largest ever catalog of these tiny galaxies. And we're going to try to do all the science questions that I try to motivate, is understand dark matter, and so on. And so just going back to the end is, each of these clumps in this dark matter simulation is one of those tiny smudges I talked about. And so with the largest ever sample, we're going to be able to really map out dark matter and what it could be at an unprecedented level. And I don't have any results to show yet, because this is as of a month old. Like, this is a very new instrument, taking very new data. And so maybe next time I'll have some new updates, we'll see. But so just to sort of have some key takeaways from this talk. Dark matter is a very fascinating topic. It makes up 85% of the material universe. So what we see, what we touch is only 15%, which is amazing and also very mysterious. Tiny galaxies have an outsized impact, I love that pun, outsized impact on our ability to answer questions regarding the nature of dark matter and how the first galaxies formed. And this is because these tiny galaxies, first of all, are one of the oldest galaxies, and so they give us a direct insight into the first galaxies themselves, and also they occupy the smallest dark matter clumps, and that's exactly where our different models of dark matter diverge. And so the hope is that we can study these tiny galaxies and get to dark matter. And the survey DESI, along with many other exciting telescopes, like Rubin, Roman, Euclid, these names you might have heard, Webb, lots of exciting stuff happening in astronomy, is already transforming and will continue to revolutionize our understanding of the universe. And so I don't know what dark matter is yet. Nobody knows. But hopefully we'll get there in the next few years. Thank you for your attention, time, and thank you to Tucker and HopMonk. Question, yes.
How many stars are in the smallest tiny galaxies?
Great question. The question was how many stars are in the smallest tiny galaxies? The smallest galaxies we know have order a few hundred stars. And for context, the Milky Way has 100 billion stars. So, big difference. Great question, yeah.
Okay. Is there a difference between globular clusters? I heard that they're just made up of really old stars. I understand, you know, the large and small magellanic clouds and maybe Sagittarius dwarf. But is there a difference between, could a globular cluster be considered a tiny galaxy?
That's a great question. The question was globular clusters, for context, are these star clusters we observe around the Milky Way. They are also very, very old, like as old as these tiny galaxies. But are they also galaxies, and where are they different? So the key difference lies in sort of a definition I did not say explicitly, but is galaxies reside in the center of dark matter clumps. Globular clusters are not like that. They are just a cluster of stars that formed. We're unclear about what the precise mechanism is, but essentially it's this giant cloud of gas that just collapsed and formed stars. While in a galaxy is you first have a dark matter clump, and that gravitationally pulls in some gas, some other stars, and that forms the galaxy. So it's a slightly different picture, but yeah. So that's the different. And also, yeah, we actually don't know yet what the smallest galaxy could be. Is there a floor? Does it continue going on even smaller? Can there be a galaxy with just one star? Is that a thing? We actually don't know. And that it gets a little tricky because the globular clusters and galaxies then tend to look quite similar star. And then you really need to infer, is there dark matter around stars we see? And that's what gets a little tricky. So yeah, it's a very big question right now is how these clusters are also connected to these tiny galaxies.
Do they spin?
You mean the stars or?
The tiny galaxies, I mean like spirals.
Ah, yes. So spiral galaxies, so they don't, as far as we know, they don't spin per se. It's very rare for them to spin. They essentially, stars are moving in random motions around this clump. So yeah, they tend to not be perfectly spinning objects. Sorry, question, yes.
Is your funding source secure?
A very timely question, yes. It is, I have the privilege of working at a well-funded private institution, and so we are better off compared to other institutions, but definitely it's an attack on astronomy as a whole, and it's real unfortunate where the priorities of the government lie. And we're all trying hard to make sure that astronomy, and not astronomy, but science in general, is secure in the future. So, yes, thank you. Yes.
In your slide of the real data from DESI, it appeared that there were filaments. Is that an illusion, like canals on Mars, or is there something else?
Very good observation. So the question was, these filaments you're seeing over here, we call them the cosmic web, but we also call them filaments. Are they real, or is that an optical illusion, as we heard before? And it is real. If you go back to the simulation picture, you see something quite similar. You see this filamentary structure. That is, we're now getting in the regime where we have so many galaxies where we can actually now just see, not really see, but see dark matter forming these cosmic web structures. So yes, that's a great observation. Yes, back there.
So the images that we get back from Jesse and Hubble and Webb, they seem to have variations in the color. And I'm wondering if the colors of these four planets and other things that we see, are they the actual colors, or are they consequences of technology that we're using?
Great question. The question was, we're seeing color over here. We see some blue, some gray, some yellow, gray maybe, yeah. So that is, I wouldn't say it's real color like what we would see, but it is real in the sense that it is indicating something physical. The color gives you an indication of the nature of the stars and the gas in the galaxy. It would tell you, it is an indication of age essentially. If it's bluer, it tends to be a little less old, and if it's sort of something like a little redder, it tends to be very old. And so when I say these galaxies are fossil galaxies, there's some, at some level they are, but there also could have recently formed stars as well. So it's sort of a mixed bag there. But so yeah, the color here is real essentially. It's sort of, it's showing you the different kinds of galaxies they are and what kind of different stars they have. I see a question back there. Yes. Ooh, do galaxies have parents? Actually, the answer is yes. So as I talked about before, let's go all the way to the back. It's the Large Magellanic Cloud and the Small Magellanic Cloud. These two are, and as we saw, our galactic backyard, as if they're orbiting around the Milky Way galaxy. We call these galaxies satellite galaxies in the sense that they're associated with a bigger Milky Way galaxy. So in a way, the Milky Way is a parent galaxy, and these tiny dwarf galaxies are their children. Yes?
So the classical view of an atom is it's extremely dense, fluidless, surrounded by an electron cloud, a probabilistic cloud, but that it's largely space. And what's in that space? Is that where dark matter lives?
So, yeah, so the question was, in our idea of an atom, there's a nucleus and there's a cloud of electrons. There's a lot of empty space in between. What is in that space? Dark matter could be there. So the thing is, dark matter is everywhere. It's also in us right now. So wherever there's space, there's dark matter. So, yes. Question?
I don't want to be a troublemaker, but you have a
Please.
circular logic here, in that you say, I calculate how fast the stars will go around the galaxy, and it's wrong. Therefore, there must be more mass. And then you make a map of the mass and call it dark matter. When I am wrong 85% of the time, I frequently question my theory at the beginning. Like, there are other theories, modified theories of gravity, and other things that could explain this 85% error. Are we absolutely certain that it's dark matter and not some mathematical error in our theory of gravity?
It's a great question. The question was, people have this theory of they modify Newtonian gravity, as we say, it's called MOND. That's an alternative explanation of what this mystic matter could be. Maybe there's just no matter at all. Maybe gravity as we know it is doing something weird at these scales. And that was a popular explanation at some point, but I think by and large right now, the community no longer believes in MOND as an explanation. And if you were to just look at the picture of stars moving and how fast they are, MOND seems compelling, but there's so many more dimensions, like so many more other evidence for dark matter. For instance, the biggest one being the cosmic microwave background, CMB. It's this map, it's the first picture of the universe. And all the statistics of this first picture of the universe is beautifully explained by a very simple dark matter model. And one could try to really squeeze in MOND there, but people have tried, it gets really messy, and dark matter just offers a much cleaner, much simpler picture. And people tend to like that more, but we still haven't found dark matter. So, you know, yeah, we'll see. Yes.
About dark matter, I'm not even really sure this is a meaningful question, but what we think about gravitational force is the deformation of the space around it, or space-time, if you will. Dark matter, if it's really matter of some type, that's yet to be described, is there anything known, or could you speculate on how or whether it does interact with the space around it in the same way or a different way?
That's a good question. So the question was, gravity, as you know it, is formed by deformation of this thing called space-time. Essentially, it's the fabric, as we say, we live in. And it's, if you put a mass, if you plop it on the fabric bends and curves, and this curve is what is called gravity. So it's sort of like, I don't know if you've seen those, like, I think in a casino, there are like these little, you drop a coin and it spins around, it goes in the middle. Just like that, it's like, the fabric itself is curved, and so if you drop something, it follows that curve and it behaves like gravity. So that's the context. So the way current models are phrased, they assume that the dark matter particle behaves with the space-time fabric in a similar way, like other normal matter. They think about these models, they try to explain is the fact that we don't see any other interaction. The gravity part is always assumed to be there, but yeah, there could be many possibilities. Dark matter also doesn't have to be one thing. That's also a thing people assume it's just one kind of thing, but it could be a whole dark sector. Sounds very cool. Like just this whole other part of the universe we just don't know what's happening. So yeah, there's lots of open possibilities, but always making the simplest assumptions first and moving on to more complex things tends to be a good approach people take. Yeah.
Just one more question?
Yes.
Just one
more
more
question. Yes, question.
In your, what you called was a recent map which showed the Earth in the center?
Yeah.
There were large black areas around it.
Ah, yes. Good point. So yes, the question was...
Is that dark matter?
Ooh, these large black areas we see, is this dark matter? Was the question? Answer is unfortunately no. This is sort of a flattened view of the 360 sky. The thing is, it did not observe every single patch of the sky. It only observed parts of the sky. And so what is darkened here are parts of the sky where it did not observe. So yeah. And I think that's it. So thank you again very much.
Thank you. I trust our speakers will hang around to answer your questions, but before we bid them both farewell, at least initially, let me ask a question of them. Perhaps some of you are curious about how these two scholars got interested in the first place in their respective sciences. So I'm going to ask Stephanie to turn her microphone back on so that she, oh joy, gets to answer this question, as well as Viraj. Okay, again, the question is, how did you get interested in this case, the eye? And how did Viraj get interested in astrophysics, or specifically tiny galaxies?
Yeah, that's a good question. Well, as you heard, I was interested in a lot of things. I was interested in speaking Russian and dancing, but I was also interested in the brain. And I felt like one way that we could study the brain is by studying vision. It's a really accessible sense in that we can really measure it and study it. And so actually a lot of what we know about the brain comes from vision scientists and neuroscientists, vision scientists. There's a lot of overlap. So I wanted to study the brain and figured I would study the eyes to do that.
Thank you.
And before I answer my question, I just realized that all laptops are more horizontal than vertical. So I was like, maybe it's that, yeah. But yeah, to answer my question, what got me into space? I think as a kid, I was always in awe of like stars and space, and I feel like at some level, it's really awesome to think about like. In our lives every day, we live on Earth and like we get stressed and life happens, but then just take a step back and think about really like where are we? It's just mind-blowing. Like the universe scale is so big. There's so many other planets out there, so many stars, so many galaxies. Just we're, as a species, so fortunate that we have evolved to be intelligent enough to answer where we came from. I feel like that's very inspiring, and that's what got me into astronomy, I guess. So, yeah.
All right. Can I ask you a question?
Oh, yes.
Did you get a chance to look through a telescope as a young person?
Yes. I recall in around, I think it was 8th grade, I was able to go on a stargazing trip, and I saw the stars. And also, one of my dad's friend had a telescope, and I was just I saw Saturn's rings. So that was also like a memory. It's a core memory, as they say. So.
Tucker, could I make a comment briefly? I was the program chair for San Francisco astronomers for 19 years, and so every month a new speaker came, including Tom A. Bell and Ralph Kaler, whose note was on there, and I asked them, because we had dinner with them before they gave their lecture in San Francisco at the Randall Museum, when did you become interested in astronomy? And I would say 85% of the speakers said, when I was a young person, I looked through a telescope. Boom, right there. So we would take our telescope, my husband and I, from Alabama, and children would look through the telescope and go, wow, what was that? I said, everyone standing in line is going to have to wait on this child because they're going to look a second time. And I know they'll end up here.
The feeling in this room was so good tonight. Thank you for being here. I want you to thank Wondernauts who are here, who have donated, HopMonk, Marin Science Seminar for co-sponsoring tonight, and, of course, Stephanie Reeves and Viraj Manwadkar.